we felt that it was very important to include the process of conducting a machine learning project in nonsense, because these are very fundamental steps that every project will have to think about. And you need to first understand how to assess the project's context, as well as the constraints, before you know which algorithms are suitable for use. If you are thinking of implementing a machine learning initiative, framing the problem should be the first step, because it will help us understand two things. Firstly, whether machine learning is able to solve the problem, and secondly, whether machine learning is the best way to solve the problem. In this video, let's find out how to frame your machine learning problem.
Have you ever seen a watchmaker at work? Starting with the movement, he carefully assembles the watch with all its moving parts, using gentle but precise movements. His tools are equally fine, suited for adjusting, attaching, and aligning. Every watch is a work of mechanical harmony, thanks to the watchmaker's skills and his tools. One day, the watchmaker loses all his watchmaking tools. In desperation, he grabs the bag of tools in his car. Those tools also adjust, attach, and align, but they're car repair tools that the watchmaker sometimes uses for general repairs around the house. Could they possibly work for watchmaking? Of course, we know that isn't possible. We may even wonder why the watchmaker would even consider such a solution. But this is the exact situation organizations often find themselves in when deciding whether to use machine learning for their business. Machine learning isn't one size fits all. Neither is it a magic pill to solve all kinds of business problems. Many noteworthy machine learning applications are very advanced and sophisticated, built for use cases that are out of the scope of everyday business needs. While machine learning can leverage the power of data to bring your organization forward, it can only do so when it is used appropriately and prudently. How do you know if machine learning is necessary for your organization? We'll get there in a while, but first, here's an overview of the 5 main areas of the machine learning process. The first area is to frame the problem properly by identifying what type of problem it is and what you really need to solve. The second area is to collect the data and prepare it to be used by the model. The third area is to select the right features or engineer them for your business use case. That is followed by selecting the right model to answer the business problem or predict something as accurately as often as possible. The final area is to evaluate the accuracy and precision of the model. We'll go in depth into each area of the machine learning process, chapter 2 and 3, but let's answer the earlier question first. How do you know if machine learning is necessary for your organization? To establish if your organization needs to implement a machine learning solution, you need to define the scope of your business problem. What is the problem, and what kind of output do you need to solve the problem? Clearly and simply articulate what you want the machine learning tool to do and achieve for your organization. This will help to structure the problem, define the goals of the initiative, and even answer the question, is machine learning necessary? Consider these 2 examples. We want to find out what our customers think about the clothes in our clothing store, versus we want to recommend customers specific clothes that they may like when they shop on our online clothing store. You'll notice very quickly the first problem statement can be solved without machine learning. Through feedback forms, interviewing, or conducting focus groups, the business can just as quickly and cost-effectively find out customer sentiment. The second statement, on the other hand, is an ideal use case for machine learning. The computer will need to analyze data like customer profiles and buying patterns to seek out patterns so that it can predict individualized solutions for each new customer. This kind of output cannot be achieved with conventional programming. If your business problem falls into any of these three scenarios, you need to predict patterns and trends based on a large volume of historical data. You need to categorize a large unknown dataset in real time. You have a situation that cannot be solved either by humans or conventional programming in a timely, cost-effective manner. Then machine learning is likely to do well as a solution for your organization. Besides defining the scope of the problem, you may also want to define what success looks like for your machine learning initiative. We're not referring to model accuracy, which we will get to in Chapter 3, but what we mean is, what is your ideal outcome? What are some measurable milestones to reach your ideal outcome? And how long do you think it will take for you to evaluate the success or failure of the machine learning initiative? Success in machine learning can be interpreted in many ways. At the fundamental level, success can be defined when the machine can outperform humans in similar tasks and if the model output is interpretable. However, there can be many ways of defining success and failure, so reaching a common understanding of what success and failure looks like with your team will help calibrate the direction of the initiative. If your machine learning initiative was able to help a bank spot fraudulent transactions 50% of the time, is it considered a success or failure? If the bank was expecting a 100% accuracy rate, then this would be deemed a failure. However, if previously the bank was only able to spot fraud 25% of the time, this may mean that the machine learning has attained some success and is heading in the right direction. Failure can also occur even if the model is successful. You may have an algorithm that is highly accurate in recommending articles to readers based on their preferences, but if the articles are all clickbait, this may not be a success metric you want. Now that you know how to define the scope of your business problem and your success metrics, how do you frame the business problem in a machine learning context? If you need a machine learning algorithm to analyze a well-labeled and well-known dataset, and then model a function that can predict future outcomes, you're looking at supervised learning, specifically classification or regression. The main difference between classification and regression are the output values. Classification will class data into discrete categories, like how a spam filtering system identifies spam and non-spam email, or an applicant tracking system knows how to group candidates who will proceed to the next level of the recruitment process, and those who were rejected at the resume stage. Regression will produce continuous values that is useful to predict numbers like future income, housing prices, and even the probability of an economic recession. Because supervised learning works with well-known and labeled data, your results are not only more reliable and accurate, you can train the machine function to produce an exact number of categories with very clear decision boundaries. You will need the time to clean the data and personnel who understand the data and can accurately label the data before analysis. This means that supervised learning cannot take place in real time or with dynamic datasets that are constantly growing in size and variety. Training and analysis need to take place offline and may not work for dynamic business problems that need the algorithm to learn in real time and continuously make improvements to the model. If you need the model to show you how to group a set of random data based on similarities without having to have a human to train the algorithm to do so, you are looking at unsupervised learning. You can use clustering or association to find these relationships in a dataset you know very little about. Clustering will produce a grouping structure for data that share similar characteristics. For example, clustering is often used in customer profiling or food delivery route allocation, or even bank fraud detection. Association rules are used to discover the probability of relationships between items in a dataset. For example, this is often used when online retailers recommend shoppers items that are commonly bought together. Unsupervised learning does not need labeled data to work, and therefore does not require any human intervention to label the data and then train it. As a result, unsupervised learning seems less complex than supervised learning. There is no predefined training structure, so computations can take place in real time, which may be helpful if you need the results very quickly. But these advantages also mean that you will not be able to specify data classes or groups. You may also face difficulty in verifying the accuracy of data, as there is no prior training of the data. If you need something to operate autonomously and decide on the best course of action, independent of human intervention, you will need to use reinforcement learning. In reinforcement learning, the machine can solve decision-making problems by independently learning the most effective decision, by simulating the task, and keeping track of which decisions ultimately result in the best performance. This is best used in autonomous vehicles, game playing, and financial portfolio optimization. Reinforcement learning tries to strike a balance between what has been done before, what worked, and what else can be done to improve the final results. Unlike the first two types of machine learning, this algorithm will try new ways of doing things and take the best course of action based on its internal feedback loop. As reinforcement learning is able to perform tasks at incredible speed, capability, and complexity, humans are still exploring the boundaries of what it can and cannot do. This means that reinforcement learning can be time-consuming, as the machine will need time to come up with strategies, execute the actions, process the feedback from its own actions, and then recalibrate its decision-making strategy. When putting together your machine learning initiative team, you may have to factor in hiring people with this specific expertise. In summary, there are 5 main areas in the machine learning process, but before we begin, we learned that it is very important to define the scope of the business problem and what success looks like to the organization. We also learned that there are 5 different problems that machine learning is typically used to solve. It could be classification, regression, clustering, association, or a decision-making output. In the rest of this course, we'll show you how 10 of the most common machine learning algorithms from all 3 types of machine learning solve problems in real-life use cases. See you at the next video, where we'll learn the importance of data collection and preparation. We've come to the end of this video. Complete the knowledge check and join us for the next video right here on Machine Learning for Humans.
People tend to underestimate the importance of the data collection and preparation phase because it can be a laborious process, and they assume that the power of machine learning lies in its cutting-edge algorithms. However, the truth is that data science is all about the data, so if the data quality is poor, even the most sophisticated analysis would generate only lackluster results. In this video, let us find out the basics of data collection and preparation.
Machine learning is fundamentally built on both the quantity and quality of data. Even if you have a lot of data, but it is low in quality, or it isn't relevant to the problem space, it doesn't matter whether you use the right algorithm or have a strong team, or you'll end up with a low-quality results. Processing the data can take up to 80% of the total time and can be quite tedious, but the investment of time will save you trouble further down the line in your machine learning initiative. Let's now learn how to collect and prepare good quality data, and what to do with bad data.
Machine learning is fundamentally built on both the quantity and quality of data. Machine learning is fundamentally built on both the quantity and quality. Machine learning is fundamentally built on both the quantity.
Machine learning is fundamentally built on both the quantity and quality of data, even if you have a lot of data. Machine learning is fundamentally
Machine learning is fundamentally built on both the quantity and quality of data. Even if you have a lot of data, but it is low in quality, or it isn't relevant to the problem space, it doesn't matter.
Machine learning is fundamentally built on both the quantity and
As we begin talking about the machine learning process, we must get one thing straight. Machine learning is fundamentally built on both the quantity and quality of data. Even if you have a lot of data, but it is low in quality, or it isn't relevant to the problem space, it doesn't matter whether you use the right algorithm or have a strong team. All you'll end up with are low-quality results. Processing the data can take up to 80% of the total time and can be quite tedious. But the investment of time will save you trouble further down the line in your machine learning initiative. Before we can even begin to understand the algorithms and models, we need to learn about the building blocks of the machine learning process. Let's start first with the data management system. Just like a gasoline engine is necessary to convert petrol into fuel to get a car moving, machine learning algorithms cannot move without the engine that converts data to be used by the machine. Here's where the data management system, a primary piece of the machine learning architecture, comes in. There are three parts to the data management system: input, processing, and output. Input is the data collected from any device or software, including your mobile phone, email client, or customer relationship management software. As the data is collected, it is stored in databases or distributed file systems. Structured data is usually stored in relational databases, such as Microsoft SQL, while unstructured data is stored in distributed file systems, such as Hadoop. Only when the data is cleaned, sorted, and processed can we start introducing machine learning models and algorithms to solve our problem statement. Finally, the output is often a number, calculating the probability or likelihood that something will happen or is true. The success of a machine learning algorithm is often evaluated through the accuracy of the output. We'll cover how to minimize errors in the output in the model evaluation in Chapter 3. There are many types of data, but let's start with the basics. Let's start with the types of data in the categorical branch. Categorical data is descriptive in nature. Some examples include hair color, marital status, and occupation. It is also possible to represent categorical data in numbers, for example using 1 for yes or 0 for no. These numbers do not possess any mathematical meanings. Under categorical data, you have nominal or ordinal data. Nominal data are used like labels for categories. They have no order like gender or languages spoken. Ordinal data is almost the same as nominal data, except that the data is always listed in order like age group, drink sizes, and competition ranking. Let's move on to numerical data. Numerical data comprises of discrete and continuous values. Discrete values represent countable categories. For example, you can have 2 children, 3 pencils, 4 sheep. Continuous values represent measurements that cannot be counted, but can be measured. For example, the height of a person cannot be counted, but it is measured by the intervals on a ruler. Temperature also cannot be counted, but only measured as intervals on a number line like a thermometer. Within numerical data, you have interval and ratio data. Interval data contains values that we can calculate the exact differences between the values. An example would be your IQ or intelligence scale or the time on an analog clock. There is no true zero, which means you don't have zero intelligence or zero time. You can add and subtract the numerical value, but you cannot multiply or divide. You cannot say that 12 o'clock is twice the number of hours of 6 o'clock. Neither can you say someone with an IQ score of 140 is twice as gifted as someone with a score of 70. Ratio data is almost the same as interval data, except that it has an absolute zero. Examples would include sales figures, income earned in a month, and years of education. Let's now talk about how to address the different parts of a spreadsheet. In a spreadsheet, which is how data is usually presented for analysis, each row is a data point, and each column is a feature. Features are also known as attributes or variables. These terms can be used interchangeably. Features are measurable descriptions of the data points collected by your input sensors. For example, if we wanted an overview of your fitness level, we would take the data from your fitness tracker and present the days you wear as individual data points. Your steps, heart rate, floors climbed, stress level, calories in and out, sleep quality would be the features that describe your overall fitness level. This entire spreadsheet would be called a dataset. It is worth noting that machine learning models typically work most effectively with numeric values. Text paragraphs, video, audio, and other unstructured data on their own don't possess much meaning. They have to be converted into numeric values so that it is easily digestible for the algorithm. There are highly advanced machine learning algorithms that can transform unstructured data into useful data. Now that we know how data works in a machine learning problem space, we can finally start talking about how to prepare data. Let's start with data cleaning. Data preparation is the crucial step to rid your data of missing, disorganized, inconsistent, noisy data. Before you begin, it is always good practice to keep a copy of the raw data and the cleaned version separately. You should perform any data cleaning or analysis on a copy of the raw data. Badly formatted data. The very first step is to check through your dataset and remove duplicate rows or columns. Correct any spelling mistakes and make sure the data follows standard formatting, especially for dates and currency. Corrupted data. This could be data that is corrupted and appear as nonsense. This will make it hard for the algorithm to understand and interpret. While it may be more straightforward to delete the bad value, consider repairing the data first. There are a number of methods you can use to repair data that are beyond the scope of this course. If you are keen to study about this topic, we've linked resources for this at the end of this lesson. If you are unable to repair the data, you may implement the same strategies to replace missing data, which we will talk about in a short while. Your last resort is to delete the value. This will reduce the amount of data available for analysis, and we know that the less data the machine can use for generalization, the less accurate your prediction may be, so delete values only as a last resort. You may also unknowingly introduce bias, as the remaining data could be skewed towards or away from particular groups. Since we're on the topic of bias, it is good that at this stage you check that the dataset is an accurate representation of the results you want. If you're trying to predict the success rate of a marketing campaign for Singaporean young women aged 18 to 25 years old, your study would be biased if you only use the data of American adult men aged 30 to 40 years old. Missing data. What if there are missing values? How can you still ensure the accuracy of the algorithm during the computation process? There are two ways you can approach this problem. 1. Data imputation. If the missing value is binary or categorical, it can be replaced with the mode of that variable. For example, if the age range is missing, you can replace that value with the most common age range. If the missing value is a discrete or continuous variable, you can replace it with the median of that variable. While this is a quick and efficient way to replace the missing values, it may not be as accurate. A more accurate but time-consuming way is to compute the data. 2. Data computation. To compute the data, more advanced supervised learning algorithms are used to estimate missing values based on similar transactions. For more information on these advanced algorithms, check out the information at the end of this lesson. Outliers. In some cases, you may have data that lie outside the norm. Sometimes these are mistakes, but they could also happen to be part of the data sample. Ignoring data that may appear as an outlier could add unnecessary bias to the data. So what can you do to check if these outliers are in fact outliers? One of the most common ways to do this is to use a box plot diagram. A box plot presents a 5-figure summary, or what we call the minimum, 25 percentile, median, 75 percentile, and maximum values. A box is drawn to connect the 25 percentile to 75 percentile, and lines extend out to the lower and upper fences. Any values that lie outside the lower and upper fences will be considered an outlier and can be safely removed. While we try not to remove data, outliers need to be removed to prevent them from affecting the final prediction result. In summary, we've covered the different types of data, what they're called in a machine learning context. We've also explained how you can clean the data so that you can effectively select or engineer the right features for your machine learning initiative. Data preparation is the most tedious and critical phase of the machine learning initiative. Doing this process well will guarantee you better returns on your investment in machine learning.
The third step of machine learning is feature selection and feature engineering. So features are descriptors for data points. In a tabular data form, we have the rows representing the data observation, a single observation, and each column will represent the feature that is corresponding to the observation. While we might be handed an original dataset that contains many features, throwing too many features into the algorithm might lead to slow computation or wrong predictions due to excess noise. So we need to shortlist the most important features. Join us as we learn more about feature selection and engineering.
Mission complete. Anything else? This won't take long.
is really interesting. This is really interesting.
Humans have the ability to visualize a two-dimension, even three-dimensional graph but anymore and it would be impossible to understand. While machines may be able to handle more
Humans have the ability to visualize a two-dimension.
Humans have the ability to visualize a two-dimension, even three-dimensional graph but any more and it would be impossible to understand. While machines may be able to handle more features. The more features you have, the longer it takes to compute. Add in irrelevant features and the machine may be trained to produce the wrong prediction output. For the algorithm to arrive at the predictive result you want as quickly and efficiently as possible, you'll need to select the right features from your dataset for analysis. How do we select the right features to use with our machine learning model? Let's find out.
The average spreadsheet these days is no longer as simple as 10 rows down and 10 columns across. Companies now have to deal with spreadsheets that have an overwhelming number of rows and columns, numbering in the thousands, even millions. Just imagine the infinite number of relationships between features that each spreadsheet would produce. Humans have the ability to visualize a two-dimension, even three-dimensional graph, but any more and it would be impossible to understand. While machines may be able to handle more features, the more features you have, the longer it takes to compute. Add in irrelevant features and the machine may be trained to produce the wrong prediction output. For the algorithm to arrive at the predictive result you want as quickly and efficiently as possible, you'll need to select the right features from your dataset for analysis. Variables, or features as they are called in machine learning, are measurable characteristics of the data sample. For example, demographics like age, gender, and geographical location are features. Features can also be as detailed as the number of exclamation points in a text or the length of a URL. The set of features is called a feature space. They are chosen in a process called feature selection, a process that is just as important as cleaning the data. Choosing a good number of features for a high-performing algorithm comes down to the type of prediction you want to solve your problem statement. If you want to find out the average age of your customers, all you require is the age attribute in your dataset. You wouldn't need to make it more complicated by adding gender, location, or educational level. But if you want to do sales forecasting, you are likely to need data on general economic conditions, product trends, size of the population, market behavior, pricing changes, amongst other things to make an accurate prediction. What we're actually doing here is assuming that these features contribute to the outcome we want. There's a relationship between the features and the outcome. We call this data correlation. Why is data correlation important? Correlation is the relationship between your features and their relationship with the output. Knowing the degree and nature of these relationships is very useful. You can easily impute missing values through predictions based on other features. Correlation is also the premise of many supervised machine learning models, like linear regression, which we'll be learning about in Chapter 4. It would be impossible to do any form of trend forecasting if your data shows no correlation. The level of correlation is always represented as a numerical range, starting at 1 for positive correlation, 0 for no correlation, and -1 for negative correlation. Positive correlation is when one feature increases or decreases, another feature also increases or decreases. For example, research has shown that the increase of body weight causes the increase of brain weight, or when someone reduces the amount of food eaten, his weight will also go down. If this correlation is strong and almost perfect, it can be represented by a value of 0.9 or 1. Otherwise, it is more likely to be between 0.5 to 0.7. Negative correlation is directly inverse. Related features don't increase or decrease together. Instead, they affect each other inversely. For example, research has shown if the number of hours spent playing video games go up, students' GPA goes down. If the number of hours go down, the GPA scores go up. If this correlation is strong and almost perfect, it will be represented by -1. But first, we need to address a problem that correlation creates. While it's tempting to assume there is causation the moment there's a high correlation, strong correlation does not mean causation. One way to avoid this is to eliminate the feature that is perfectly correlated. You can also use certain machine learning techniques to do feature selection and at the same time avoid perfect correlation. One such technique is called Principal Component Analysis, or PCA. PCA helps to reduce the number of columns or features that the machine has to analyze while still preserving most of the information from the dataset. In machine learning terms, this process is called dimension reduction. There are quite a few mathematical formulas for PCA, and we will include more information on these at the end of this lesson. In short, PCA works by grouping similar features together to reduce the number of individual features, or principal components, used for comparisons. For example, if you are looking at the data of a supermarket chain, you may have the following information: size, total number of families in neighborhood, number of aisles, number of counters, number of competitors in neighborhood. There are 5 features, and now I want to reduce this number. How can I do this? Right away, you can see that if we rearrange the components, we have 2 distinct groups. The components in the first group are all related to the size of the supermarket. The more aisles and counters a supermarket has, we can safely assume the bigger it is. So the first group can be labeled size, and the second group will be location, since all the features in the second group are related to the location of the supermarket. We don't need all the components within each group, so we may use the weighted sum of all the components within each group to get a principal component, which is a representative feature in place of the original features. Feature selection is just about selecting or removing features for analysis. We don't change the inherent data at this stage. There are even higher level algorithms such as Lasso that can not only select your features, but also reduce the error present in your algorithm. However, there are times when the best features need to be engineered. The last step of the data preparation phase is feature engineering. Feature engineering is about creating new features from raw data that are more aligned to solve the predictive output problem. This will not only help the model to learn better, it will also increase its accuracy. Here's an example. To predict traffic on a given day at a specific time, you may have information like the date, time, and vehicle speeds. Right now, the date and the time doesn't mean very much. It may be more meaningful to transform this column into two separate columns, day of the week and hour of the day. The reverse is true also when there are too many insignificant features that may benefit from being combined. For example, to predict whether a subscriber on your email list will purchase something at your next launch, you have the subscriber's first name, middle name, last name. Each feature doesn't mean anything to the prediction, so it might be more effective to combine all three columns into a single column as such. You can also use feature engineering when you want to reduce the number of unique values within each feature column. A school wants to give out various study grants to needy students in the school. The type of grant the students will get depends on their monthly household income. Instead of dealing with an infinite number of continuous values when it comes to the student's monthly household income, it may be more meaningful to bin the values or classify them into broader categories like this. This is helpful to discover sets of patterns in the continuous data, which may be difficult to analyze if left as continuous values. There is no standard rule for the bin size, and data experts often use previous experience with similar situations to come up with the right bin size. However, binning may not always be the answer. With binning, you inevitably lose information which may affect the final model. Binning also will not work on regression problems. For example, if we wanted to predict the future incomes of these needy students based on their current monthly household incomes, we need to have each data value represented to come up with a more accurate prediction. There are more advanced feature engineering techniques like log transform, which we will not be covering in this course. In short, feature engineering will help the machine learning algorithm generalize the conclusion and prevent overfitting, which is a topic we'll discuss in Chapter 3. In summary, if machine learning is all about finding the patterns and trends in data, then the correlation between variables is the fuel for this to happen. With spreadsheets these days that could go up to more than a few thousand rows down and columns across, the relationships between variables could be infinite. If we put all these into the machine, it would take too long, be computationally too expensive, and may cause too many errors in the outcome. For a successful outcome, we need to select the most crucial features for each specific initiative. While it seems straightforward to choose features with the highest correlation rate, a very high rate of correlation may actually lead to an output that you can't generalize on a wider scale. It is therefore crucial to know how to select the right features for the algorithm, and if the features need some engineering to become even better for analysis. We've come to the end of this video. Complete all activities listed for this chapter, and we'll see you at the next chapter, right here on Machine Learning for Humans. The average spreadsheet these days is no longer as simple as 10 rows down and 10 columns across. Companies now have to deal with spreadsheets that have an overwhelming number of rows and columns, numbering in the thousands, even millions. Just imagine the infinite number of relationships between features that each spreadsheet would produce. Humans have the ability to visualize a 2-dimension, even 3-dimensional graph, but any more and it would be impossible to understand. While machines may be able to handle more features, the more features you have, the longer it takes to compute. Add in irrelevant features, and the machine may be trained to produce the wrong prediction output. For the algorithm to arrive at the predictive result you want as quickly and efficiently as possible, you'll need to select the right features from your data set
Well, the
for
first month is
analysis.
$1.
Variables,
$10 a month,
or
you pay
features,
$10.
as they are
Like
called in machine learning, are measurable characteristics of the data sample. For example, demographics like age, gender, and geographical location are features. Features can also be as detailed as the number of exclamation points in a text or the length of a URL. The set of features is called a feature space. They are chosen in a process called feature selection, a process that is just as important as cleaning the data. Choosing a good number of features for a high-performing algorithm comes down to the type of prediction you want to solve your problem statement. If you want to find out the average age of your customers, all you require is the age attribute in your dataset. You wouldn't need to make it more complicated by adding gender, location, or educational level. But if you want to do sales forecasting, you are likely to need data on general economic conditions, product trends, size of the population, market behavior, pricing changes, amongst other things to make an accurate prediction. What we're actually doing here is assuming that these features contribute to the outcome we want. There's a relationship between the features and the outcome. We call this data correlation. Why is data correlation important? Correlation is the relation The average spreadsheet these days is no longer as simple as 10 rows down and 10 columns across. Companies now have to deal with spreadsheets that have an overwhelming number of rows and columns, numbering in the thousands, even millions. Just imagine the infinite number of relationships between features that each spreadsheet would produce. Humans have the ability to visualize a 2-dimension, even 3-dimensional graph, but any more and it would be impossible to understand. While machines may be able to handle more features, the more features you have, the longer it takes to compute. Add in irrelevant features, and the machine may be trained to produce the wrong prediction output. For the algorithm to arrive at the predictive result you want as quickly and efficiently as possible, you'll need to select the right features from your dataset for analysis. Variables, or features as they are called in machine learning, are measurable characteristics of the data sample. For example, demographics like age, gender, and geographical location are features. Features can also be as detailed as the number of exclamation points in a text or the length of a URL. The set of features is called a feature space. They are chosen in a process called feature selection, a process that is just as important as cleaning the data. Choosing a good number of features for a high-performing algorithm comes down to the type of prediction you want to solve your problem statement. If you want to find out the average age of your customers, all you require is the age attribute in your dataset. You wouldn't need to make it more complicated by adding gender, location, or educational level. But if you want to do sales forecasting, you are likely to need data on general economic conditions, product trends, size of the population, market behavior, pricing changes, amongst other things to make an accurate prediction. What we're actually doing here is assuming that these features contribute to the outcome we want. There's a relationship between the features and the outcome. We call this data correlation. Why is data correlation important? Correlation is the relationship between your features and their relationship with the output. Knowing the degree and nature of these relationships is very useful. You can easily impute missing values through predictions based on other features. Correlation is also the premise of many supervised machine learning models, like linear regression, which we'll be learning about in Chapter 4. It would be impossible to do any form of trend forecasting if your data shows no correlation. The level of correlation is always represented as a numerical range, starting at 1 for positive correlation, 0 for no correlation, and -1 for negative correlation. Positive correlation is when one feature increases or decreases, another feature also increases or decreases. For example, Research has shown that the increase of body weight causes the increase of brain weight, or when someone reduces the amount of food eaten, his weight will also go down. If this correlation is strong and almost perfect, it can be represented by a value of 0.9 or 1. Otherwise, it is more likely to be between 0.5 to 0.7. Negative correlation is directly inverse. Related features don't increase or decrease together. Instead, they affect each other inversely. For example, research has shown if the number of hours spent playing video games go up, students' GPA goes down. If the number of hours go down, the GPA scores go up. If this correlation is strong and almost perfect, it will be represented by -1. But first, we need to address a problem that correlation creates. While it's tempting to assume there is causation the moment there's a high correlation, strong correlation does not mean causation. One way to avoid this is to eliminate the feature that is perfectly correlated. You can also use certain machine learning techniques to do feature selection and at the same time avoid perfect correlation. One such technique is called Principal Component Analysis, or PCA. PCA helps to reduce the number of columns or features that the machine has to analyze while still preserving most of the information from the dataset. In machine learning terms, this process is called dimension reduction. There are quite a few mathematical formulas for PCA, and we will include more information on these at the end of this lesson. In short, PCA works by grouping similar features together to reduce the number of individual features, or principal components, used for comparisons. For example, if you are looking at the data of a supermarket chain, you may have the following information: size, total number of families in neighborhood, number of aisles, number of counters, number of competitors in neighborhood. There are 5 features, and now I want to reduce this number. How can I do this? Right away, you can see that if we rearrange the components, we have 2 distinct groups. The components in the first group are all related to the size of the supermarket. The more aisles and counters a supermarket has, we can safely assume the bigger it is. So the first group can be labeled size, and the second group will be location, since all the features in the second group are related to the location of the supermarket. We don't need all the components within each group, so we may use the weighted sum of all the components within each group to get a principal component, which is a representative feature in place of the original features. Feature selection is just about selecting or removing features for analysis. We don't change the inherent data at this stage. There are even higher-level algorithms, such as Lasso, that can not only select your features, but also reduce the error present in your algorithm. However, there are times when the best features need to be engineered. The last step of the data preparation phase is feature engineering. Feature engineering is about creating new features from raw data that are more aligned to solve the predictive output problem. This will not only help the model to learn better, it will also increase its accuracy. Here's an example. To predict traffic on a given day at a specific time, you may have information like the date, time, and vehicle speeds. Right now, the date and the time doesn't mean very much. It may be more meaningful to transform this column into 2 separate columns, day of the week and hour of the day. The reverse is true also when there are too many insignificant features that may benefit from being combined. For example, to predict whether a subscriber on your email list will purchase something at your next launch, you have the subscriber's first name, middle name, last name. Each feature doesn't mean anything to the prediction, so it might be more effective to combine all 3 columns into a single column as such. You can also use feature engineering when you want to reduce the number of unique values within each feature column. A school wants to give out various study grants to needy students in the school. The type of grant the students will get depends on their monthly household income. Instead of dealing with an infinite number of continuous values when it comes to the student's monthly household income, it may be more meaningful to bin the values or classify them into broader categories like this. This is helpful to discover sets of patterns in the continuous data, which may be difficult to analyze if left as continuous values. There is no standard rule for the bin size, and data experts often use previous experience with similar situations to come up with the right bin size. However, binning may not always be the answer. With binning, you inevitably lose information which may affect the final model. Binning also will not work on regression problems. For example, if we wanted to predict the future incomes of these needy students based on their current monthly household incomes, we need to have each data value represented to come up with a more accurate prediction. There are more advanced feature engineering techniques like log transform, which we will not be covering in this course. In short, feature engineering will help the machine learning algorithm generalize the conclusion and prevent overfitting, which is a topic we'll discuss in Chapter 3. In summary, if machine learning is all about finding the patterns and trends in data, then the correlation between variables is the fuel for this to happen. With spreadsheets these days that could go up to more than a few thousand rows down and columns across, the relationships between variables could be infinite. If we put all these into the machine, it would take too long, be computationally too expensive, and may cause too many errors in the outcome. For a successful outcome, we need to select the most crucial features for each specific initiative. While it seems straightforward to choose features with the highest correlation rate, a very high rate of correlation may actually lead to an output that you can't generalize on a wider scale. It is therefore crucial to know how to select the right features for the algorithm, and if the features need some engineering to become even better for analysis. We've come to the end of this video. Complete all activities listed for this chapter, and we'll see you at the next chapter, right here on Machine Learning for Humans.
Let me share a story about a project that was done by the Government Technology Agency of Singapore, or GovTech for short, as well as the Singapore Police Force. So the police force approached GovTech to build an artificial intelligence model for database search. The problem was that an officer would take up to 20 minutes for a single search, which was considered slow, so they wanted to have a model that could intelligently piece together information about a suspect from multiple databases as quickly as possible. So GovTech, they looked at the problem, they went to interview a few police officers and found out that actually the police officers were quite good at piecing information together from different sources. Just imagine yourself going to LinkedIn, you find out where a person worked, and then you go to Instagram to find out what the person ate for dinner last night, and you piece them up together. It is not a cognitively difficult task that requires machine learning or artificial intelligence. So the problem was that the police force, they had multiple databases, and the officers had to log into each one of them to search the databases. And another problem was that the speed engine was slow. So GovTech identified these problems, and what they did was they optimized the search function, improve user interface, make it more intuitive, and the result was that database searches now took less time. So it was indeed fortunate that GovTech was able to frame the problem well in this case. If you want to find out more about what they did, you can visit their website. But the key lesson learned here is that machine learning is just one tool out of many tools to solve a problem, and it may not always be the best tool. So understanding how machine learning works and understanding the specific context of the problem will help you evaluate whether machine learning is the best tool. Well, firstly, you should frame the problem before you even start building your model or collecting your data, because the data you collect will very much depend on the problem at hand. Secondly, be as specific as possible the problem you're trying to solve, or the outcome or business goal you're trying to achieve. And thirdly, after framing the problem, understand whether machine learning is able to solve the problem and whether machine learning is the best way to solve the problem. companies should have manpower and infrastructure dedicated to maintaining databases. So databases are necessary to enable automatic storage and easy retrieval of data while ensuring that data inputs are formatted suitably and consistently for analysis. An online retailer like Amazon would amass large amounts of user data, such as when a user browsed and purchased a product, or even when they browsed but did not purchase the product. So these data points are processed in real time and used as a feedback to generate product recommendations that appear on a user's Amazon homepage. So this is a personalization that's based on the user's browsing history. Another point is that machine learning applications are made possible through collaboration between the data engineers and the data scientists. So data engineers are people who maintain databases from which data is fed into the machine learning algorithms. Well, firstly, ensure that whoever is collecting your data understands the importance of formatting and having minimal missing values. So there was this data set that I encountered, and in one of the columns there were numbers. But someone decided that the best way to encode these numbers was to write it out in letter form. So instead of having 1, 2, 3, it will be like ONE, TWO, and so on. And while this may seem perfectly reasonable to whoever was collecting the data, it makes no sense from the data scientist's perspective at all, because the numeric form is the best way to analyze the data. Secondly, you should understand how your data was collected and whether there are any biases that appear within the data because of the way it was collected. Lastly, you should be prepared that your model may require more data in the future. So always think about how your data collection methods can be sustainable. Most of the time, there is value in engineering certain features. For example, if you want to predict who will resign from your organization, you have human resources data. And let's say you have 3 features. You have salary, you have years in service, you have performance grade. So intuitively, you will make use of salary to build your model, right? For example, if you know that someone is not earning high salary, then they might quit and they might look for opportunities elsewhere. But then our model will be biased in predicting the entry-level employees as most at risk for quitting. So a more realistic predictor for resignation would be to combine the salary data as well as the years in service data to see what is their salary increase rate. And we can also engineer features to review changes in performance grade over time. And perhaps you can see that perhaps some people are lacking motivation at the point of resignation. Firstly, you should try to understand how the different features, how they relate to each other. And this will help you to decide whether you need to modify or select certain features. If some features are very strongly correlated, you may also wish to remove them to see if it improves your model. Secondly, understand the distribution or shape of your data points for each of your feature, because this will help you to decide whether you need to perform feature engineering. Let me give you an example. If we have income data, you'll probably look a bit like this. The data will be skewed such that the top earners are earning much more. But if you think about having one person earning 100K a month and another person earning 5K, the first person is not going to purchase 20 times more groceries than the second person. So the more meaningful analysis will be to group people together. For example, the top 10 percentile will be one group, the 10 to 20th percentile is in another group, and so on. So we have 10 groups, and this is called binning. So feature engineering is sometimes grouped under data preparation because it is part of the same effort to convert data into suitable inputs for algorithms. And data engineers will pre-calculate important features and store them in databases so that they can be easily extracted by data scientists train the machine learning models. And you can see here that the synergy between data engineers and data scientists are again apparent, because data scientists will have to keep the data engineers updated on newly discovered features to include in the databases. After expanding the number of features available through feature engineering, we need to shortlist the features to eventually include in our machine learning model. Some models, such as neural networks, have a built-in feature selection capability, where features with stronger predictive power are given heavier weight, while less predictive features are excluded. So, while this automatic feature selection is convenient, we must not be complacent. For instance, predictive policing tools have been found to target minority racial groups unfairly. And this is because the model is given free rein to use any features. So it may gloss over core predictors such as income and education level, and instead it is misled to focus on a correlated feature such as race. So therefore, when we select features, we should not only account for how the features improve the prediction accuracy, but also strive to identify which features have been included and to what extent, so as to avoid the biased results that could have dire consequences. for the algorithms which we are going to learn in subsequent chapters, these are usually standard algorithms which are not actually built from scratch, and a lot of them can be purchased off the shelf. We just need to customize them by deciding the algorithms to use as well as the hyperparameters to select from. Model selection is deciding the kind of model that we want that can best suit our business objectives and the outcome we hope to achieve. Let's find out how to effectively select the right machine learning model for your business problem.
With so many machine learning models available in the market today, how do you technically know which one of the supervised machine learning models is the most accurate of the lot? Cross-validation is used in the industry as a relatively easy to understand and easy to implement process that could help you estimate the skill of your predictive machine learning model. Let's now find out how to use cross-validation to select the right model for your problem.
By now, you may have shortlisted a few models based on your business needs. Supervised learning is typically what most organizations will start with before moving on to the other types of machine learning. So, how do you technically know which one of your supervised machine learning models is the most accurate of the lot? Cross-validation is used in the industry as a relatively easy to understand and easy to implement process that can help you estimate the skill of your predictive machine learning model. The first step of cross-validation is to split your dataset into two types of data. A classic way of dividing the data is 80% training data and 20% test data. Training data is used to train the model. None of this data should be used as test or validation data. Test or validation data is used solely for the purpose of objectively evaluating the performance of the trained model. There are various schools of thought on what the ideal split between training versus test data should be, but most say the 80-20 split is applicable to most situations. Contrary to popular belief, machine learning training algorithms are not always built from scratch. It would be too expensive and unnecessary, as there are already pre-built solutions in the market that organizations can put to work immediately. Data professionals actually recommend that more time be spent with feature selection, which occurs before the training, and fine-tuning the parameters for the prediction, which occurs after the training. This is done through a process called cross-validation. There are many cross-validation strategies available, but in this course we will focus on one called simple K-folds. K-folds is recognized as being easier to understand and less biased compared to other models. It is also more reliable, especially if you have a smaller dataset. We'll explain why in a moment. What is the K in K-folds? K refers to the number of parts you want to split your dataset into for training and testing. Like other instances of K in this course, the value shouldn't be too big or too small. Data professionals generally like to peg the value of K to the size of their dataset, keeping it between 5 and 10. So, how does K-folds work? Here's how. Let's assume K equals 5, and you have 500 instances or examples in your dataset. Since K equals 5, you will split the data randomly into 5 equal folds or parts. We will be explaining how to conduct one run of cross-validation for one machine learning model. Depending on how many shortlisted models you have, you will rerun the same process for the other models. In the first iteration, part 1 to 4 will be trained on the model, and part 5 will be used to test. Retain the model evaluation score. In the second iteration, part 2 to 5 are trained, and part 1 is used to test. Again, the evaluation score is recorded. In the third iteration, part 1, 3, 4, 5 are trained, and part 2 is used to test. This process will continue until all 5 iterations are done and all the parts have been used for training and testing at least once. Once you have completed all the iterations, the performance is demonstrated by taking the average of all the evaluation scores. This is an advantage, especially if you have a small dataset. For example, if you have only 100 instances in your dataset and you do the classic 80-20 split, you'll end up with only 20 instances for your test data. This is too small to draw a fair and objective judgment of your data. Using k-folds means that you don't need to only test on 20% of your dataset. Because of the iterative process of training and testing, you can evaluate the performance of your model with 100% test data. The reason why this is supervised is because both the input and output data are well known by the machine. This is akin to the machine acting like a teacher who is marking the results of her math test with an answer key. K-folds is also a great strategy to overcome overfitting of your data. What is overfitting? We'll get to that in a bit. At this
I'm ready to go.
You're here, Captain.
Leave it to me. Ugh. Your bag looks pretty heavy.
You look great.
Ugh. Your bag looks pretty heavy. This is the safest place in the world.
Captain, you made it.
We're here.
At this point, you might be wondering, I know how to train and test the model, but what do you mean by evaluation? There are two key metrics to gauge a machine learning model's performance. First, we look at the accuracy of the prediction, and second, how well the model generalizes on an independent test dataset. In short, the machine learning model you select for your business problem should be able to predict an output that is as close to the actual data. However, all machine learning models come with a certain level of error. Error is caused by the bias and variance in the data. Bias occurs when the model learns to make wrong assumptions of the data because it did not take into consideration all the information present in the data. Variance is the direct opposite, when the model becomes too sensitive to the training data that it becomes inflexible to new data. High variance produces an output that too closely resembles the training data, rather than being able to generalize to the context of the independent dataset. Together, bias and variance can cause the underfitting or overfitting of data. If the model contains high bias, it is called underfitting. Underfitting means that the model is failing to register significant trends in the data. In other words, it is too simple to explain the variance in the data. As a result, the output will experience high training error and test error. If a model contains high variance, it is called overfitting. Overfitting means that the model is so well trained on the training data that it is no longer applicable to test data. As a result, the output will experience low training error but high test error. While 100% accuracy is desirable, perfection can actually lead to your model being less effective. Be careful of training the data until yields perfect results. What defines a model with good fit then? When a model demonstrates good fit, it is able to generalize similar predictive outcomes with minimal error on both the training and test data. We'll talk about how to evaluate accuracy in the next video. So, is there a way we can solve underfitting and overfitting then? Underfitting can be solved by increasing the overall complexity of the model, or obtaining more features, or increasing the number of iterations the model is run. Overfitting is a constant concern for most studies, but it can be solved by including more data points, using less features, or decreasing the complexity of the model. Parameter tuning is also a key method to balance the complex relationships between the input variables and the output. This results in more accurate predictions made on a consistent basis. We will talk more about parameter tuning in the next video. In summary, we learned how to select the right supervised learning model for your machine learning initiative. After shortlisting a few algorithms you want to use, it is essential to conduct cross-validation to check if the models fit your data well. An easy and more accurate way to do is k-folds cross-validation. By dividing the data into a defined number of folds or groups, you can effectively train and test your model on 100% of your data instead of only a smaller portion of data. However, all machine learning models suffer from a certain level of error caused by bias and variance. This is seen through a large disparity between training and testing data in terms of accuracy. When the model contains high bias, it is oversimplified and misses what most of the important relationships in the training data. This is known as underfitting. When the model contains high variance, it becomes overly sensitive to the random fluctuations of the training data that it is inflexible to generalize a prediction for new data. This is known as overfitting. While underfitting and overfitting are troublesome for machine learning teams, they can be resolved through various methods, one of which is parameter tuning.
Freaking Tinos. They're tougher than they look. Don't let them pull out your hair. Welcome, Captain. can't fit everything in here. What would you like me to hold on for you? You?
The light will guide us. Is this everything. I'll see you later.
I'm back. I'm back.
I'm glad I could help. Look what I found! I'll do what I can to be of service.
I'm heading out. I'll be right back, Captain.
Model evaluation allows us to have a goal to work towards. It will help us to compare the performance of different models relative to the chosen evaluation metric. It is important to note that your models may be ranked differently depending on the chosen metric. As such, it is important that the chosen metric fits the outcome or business goal that we are trying to achieve, which should have been defined in the problem framing. Sometimes we may even choose more than one metric to evaluate our models. It is a crucial step of the machine learning process, and for good reason. Let's find out more about how you can evaluate your model to make sure it produces the right output for you.
Translate. Upcoming change. Imagine if a tumor much as it costs to mount a machine learning initiative, it may cost much more if the errors in the machine learning model are left unchecked. Imagine if a tumor detection machine identified healthy tissue as cancerous and cancerous tissue as healthy tissue. Or if predictive devices on police officers identify an approaching stranger as armed and dangerous, but the person is only trying to seek help. Knowing how to evaluate model results is very important, so in this video, let's find out how. Send feedback. History. E-devices on Home Tools Notepad. Cost much more if the
Errors in the machine. Learning model are left unchecked. Imagine if a tumor detection machine identified healthy tissue. Tissue as cancerous and Imagine if a tumor detection machine identified healthy tissue as cancerous and cancerous tissue as healthy tissue.
Or if predictive devices on police officers identify an approaching stranger as armed and dangerous, but the person is only trying to seek help. Knowing how to evaluate Imagine if a tumor detection machine identified healthy tissue as cancerous and
As much as it costs to mount a machine learning initiative, it may cost much more if the errors in the machine learning model are left unchecked. Imagine if a tumor detection machine identified healthy tissue as cancerous and cancerous tissue as healthy tissue. Or if predictive devices on police officers identify an approaching stranger as armed and dangerous, but the person is only trying to seek help. Both instances are extreme, but they represent the incredibly high cost when error is present in machine learning algorithms. The only way that machine learning can help and not harm is to make sure that it is performing with the lowest possible error. In the previous video, we discussed bias and variance. While both are perceived negatively when applied to machine learning individually, it is possible to decrease error by balancing the bias and variance together. This is called the bias-variance trade-off. High bias occurs when there are too few parameters in place, resulting in an oversimplified model. High variance is a result of having too many parameters in place, resulting in an overly complex model. By turning the knob to control the parameters, just like how you would turn the knob on a radio to adjust the frequency to reach a station you like, you can actually balance out the bias and variance to produce a model with higher accuracy and better reliability. We've introduced a new word here, parameters. Just what are they? Parameters are configurable variables that can be estimated from the training data. These include weights or coefficients that better help the model to fit the data. Most machine learning models contain inbuilt mechanisms to optimize these parameters. At a higher level, hyperparameters control the complexity of the training process itself. In artificial neural networks, this could mean how many hidden layers should be used in the algorithm or in decision trees. What is the optimal number of splits in the nodes? These cannot be estimated from the training data. Instead, hyperparameter tuning is done by data scientists who rely on their experience and domain knowledge to skillfully find the right balance and level of complexity. If parameters are well tuned, the model is able to find the sweet spot between highlighting major trends while discounting minor variations. Different algorithms will have different parameters available for tuning. Depending on how the parameters are tuned, a single algorithm can generate different, varying results. As such, tuning the parameters increases the opportunity to build a vast number of potential models to suit every business problem. Now that we've talked about how to tune parameters to increase the accuracy of the machine learning model, let's discuss how to discern the accuracy of a model. To evaluate any technique, we generally look at three important aspects. The first is the ease of interpreting output. The second is the calculation time, and the third aspect is the model's predictive power. We also use evaluation metrics which are used to compare how accurate models are in their predictions. They will differ in how they define and penalize different types of prediction errors. Let's begin with the simplest metric for classification problems called the percentage of correct predictions. It is represented in a formula that calculates the number of correct predictions over the total number of predictions. Technically, this formula gives you the proportion of correct predictions, but it doesn't specify what was predicted correctly and incorrectly. This could lead to some serious consequences, as seen in this example. Let's say we want to calculate the accuracy of a model that classified 100 tumors as malignant or benign. Using the formula above, the accuracy comes out to 0.91 or 91%. That is, 91 correct predictions out of 100 total examples. Seems like our model has a high accuracy rate, right? But if we dig into the actual data, we'll find that of the 100 tumor examples, 91 are benign and 9 are malignant. The model correctly identifies 90 as benign and 1 as malignant. This means that out of the 9 malignant tumors present, the model only correctly identifies one as malignant. How about the other 8 malignant tumors that go undiscovered? The costs of failing to diagnose a malignant tumor would be infinitely more than sending someone with a benign tumor for more tests to ascertain the type of tumor he has. This evaluation metric is accurate on a certain level, but it doesn't reach the kind of accuracy or specificity needed for accurate decision making. So simple is good, but it isn't the best. This next evaluation metric builds on the previous one by providing further insight into where the prediction model succeeded and where it failed. It is called the confusion matrix. Don't be fooled by its name. The matrix actually helps to dispel the confusion, especially in situations where distinguishing the type of prediction error is crucial. The confusion matrix is used for classification problems. Presented in a 2x2 table, it contains 4 possible outcomes of predicted and actual values. True positive means it is predicted positive, and the actual data is indeed positive. This is a person who thinks he has a malignant tumor, and he indeed has one. True negative means it is predicted negative, and the actual data is negative. This is a person who thinks he doesn't have a malignant tumor, and he indeed doesn't have one. False positive means it is predicted positive, and the actual data is negative. This is a person who thinks he has a malignant tumor, but he doesn't have one. False negative means it is predicted negative, and the actual data is positive. This is a person who thinks he doesn't have a malignant tumor, but he indeed has one. The confusion matrix works by calculating 2 factors: recall and precision. The differences are very subtle and easy to miss, but let's use the example to make it clearer. Recall is the proportion of correct predictions among all the test data that were actually positive. This is the number of people who were currently predicted to have a malignant tumor among all the people who actually have a malignant tumor. It is derived by dividing the number of true positives by the number of true positives and false negatives added together. Precision is the proportion of correct predictions among all the test data that was predicted as positive, whether true or false. That is the number of people who actually have a malignant tumor among all the people who were predicted to have a malignant tumor. It is derived by dividing the number of true positives by the number of true positives and false positives added together. However, recall and precision cannot individually give you the specific accuracy you need. You need to compare both factors together in what we call an F measure. It is represented in this mathematical formula. The confusion matrix is particularly useful in crucial situations where a false negative is far costlier than false positives. You would rather spend the money on more tests to ascertain the true nature of your tumor than to falsely believe that the tumor you have is benign. The third evaluation metric is popularly used for regression problems. It is called root mean squared error, or RMSE. If error is the difference between the actual and predicted value, RMSE, as a mathematical formula, will give you how far the average error is going to be. The smaller the difference, the better and more accurate your prediction will be. But there is really no standard answer to what an acceptable range of error is. A data scientist will use experience, or what we call heuristics in machine learning, to decide what is an acceptable range of error, which may differ from problem to problem. The downside of RMSE is that each individual error is squared, amplifying large errors. This means that the metrics becomes extremely sensitive to outliers, and that can severely penalize the model's performance. In summary, we discovered what parameters are and why tuning them, like on the knob of a radio to find the frequency of the station you like, can actually improve the performance of the model. While there are standard algorithms used across the machine learning environment, engineering features and tuning parameters is what makes a standard algorithm customized to support the needs of your business problem. However, parameter tuning is more an art than a science. Finding the right balance between complexity and generalization comes down to heuristics, or what we call prior experience of the data expert. Once you have found the right balance, it is time to evaluate the accuracy of the model using a set of metrics. In this course, we introduced 3 types: percentage of correct predictions, confusion matrix, and root mean squared error. Of course, there are many more types of evaluation metrics, like area under the ROC curve, concordant, discordant ratio and gain and lift charts that we haven't covered in this course. As you develop in your machine learning journey, you may want to look into these other metrics as well. Also, depending on the aims of your machine learning initiative, new metrics could be designed to penalize and avoid specific types of errors. The bottom line when it comes to evaluation metrics is that the evaluation metrics you choose should be based on the model you use, the type of business problem, and the predictive output you need. But evaluation metrics shouldn't be used on the model alone. As we mentioned earlier in this chapter, feature engineering and parameter tuning can actually help to improve the model's performance and get excellent results from the evaluation metrics. With this, we round off the 5 steps that every machine learning team will go through to launch a machine learning initiative. In the next few chapters, we will explore how 10 of the most commonly used machine learning techniques work. We've come to the end of this video. Complete all activities listed for this chapter, and we'll see you at the next chapter, right here on Machine Learning for Humans.
There are 2 key aspects here: cross-validation as well as diagnosing any problems with your model. So cross-validation is applicable for supervised learning and reinforcement learning, and it measures how well your model will perform against a totally new data set, how well it can generalize. The thing about machine learning is that we can very easily build a model that can give 100% accuracy on the training data we feed the model because we give the model the correct answers. So think of it as administering school examinations based on practice questions for which the answers have been given to students. And the students are very likely to perform well because they have seen the questions and answers. We take away the answers and we give them completely new questions to the students. This is something called cross-validation. And we will be able to see how well our student performs based on what they have learned previously. Another important aspect is to look at the model results and the output and see whether the results make sense. So sometimes our model is not working because we have not set it up properly. So we just need to retry the model. Sometimes our model is not complex enough and we cannot reach the desired level of accuracy. Sometimes our model doesn't generalize well, so we need more data points. So studying the model results is quite essential in understanding how we can further improve the model in our next iteration. In practice, however, there are other factors to consider such as accuracy and complexity. For instance, neural networks are very accurate, but are also notoriously complex. Overly complex models are bad because not only are they slow and expensive to compute, they are also much more difficult to calibrate. Calibration is important because features and models might change over time. Take fashion trends, for example. A recommendation engine for clothes would have to account for changing fashion styles. So what we want from a model is high accuracy and low complexity. There is also the problem of ethics, whereby certain fields such as law, justice, and healthcare, it is very important to know how the model made the conclusion. So overly complex models may have better accuracy, but often they do not tell you the specific steps as to how the model get from the input to the output. We call these black box models because we cannot see what is inside the model, and these models present ethical issues. I would say that firstly, you need to understand the different evaluation matrix that are available, so that you have more options to choose from and you can choose the best option. There are also different metrics for classification and regression problems. Secondly, sometimes it is best to keep it simple depending on the audience you are presenting to, so that your audience understands how the model was evaluated and why it will fit the business goals. Models are evaluated using matrix, so choosing the right matrix is very crucial. For example, if you are trying to predict risk scores for credit card fraud, prediction accuracy would be a bad metric. Because most credit card transactions are legitimate, you can simply label all of your transactions as non-fraud, and you might still end up with an accuracy of over 99%. For such imbalanced datasets, you'll be better off using precision or recall as the evaluation metric. And even choosing between precision and recall is often a business decision. The precision matrix strives to minimize false positives, so it is useful in applications like predictive policing, where you want to avoid wrongly convicting someone. On the other hand, the recall matrix aims to minimize false negatives, so it is useful in applications like healthcare, where it is highly risky to let a contagious disease go undetected.
cancerous tissue as AC Study 1 Uber Technologies. About the organization Uber Technologies, Inc. is an American multinational transportation network company, TNC, offering services that include peer-to-peer ride-sharing, ride service hailing, food delivery, bicycle sharing, and more. The company is based in San Francisco and has operations in over 785 metropolitan areas worldwide. As of 2019, Uber is estimated to have 110 million worldwide users, a 69% market share in the United States for passenger transport, and a 25% market share for food delivery. Problem framing. From the myriad of its service offerings in the United States, Uber receives millions of support tickets every week from riders, drivers, eaters, freighters, and users of other Uber services. Due to the scale of its operations, managing the sheer volume of support tickets is already a daunting challenge. To further complicate matters, Uber has to deal with the complexity of the thousands of different support issue types as a result of its wide variety of service offerings. Desired outcome. Clearly cognizant of this issue, Uber set in motion its grand plan to reduce the overall support ticket handling time across its business lines. To tackle the issue up front, Uber decided to adopt machine learning to effectively classify the large volume of support tickets, so that relevant support functions can immediately follow up to resolve the issues and close the tickets. The envisioned outcome is an automated customer service representative enabled by machine learning customer obsession ticket assistance (COTA). One implementation. Uber's applied machine learning (AML) team undertook the task to create COTA. The AML team first identified all the key data sources that are essential as inputs for COTA, namely, user information, for example name, user type, etc., service information, for example ride information such as ETA, location, etc., ticket metadata, for example creation time, product type, etc., ticket message. The information is then pre-processed to be used as inputs for its natural language processing and machine learning models. After multiple rounds of model training and enhancement, Uber managed to make COTA a success. Final outcome. COTA yielded an 8.8% reduction in the average handling time of support tickets, which directly means that Uber's customers can get their tickets resolved much faster. More importantly, Uber managed to achieve this success without compromising existing levels of customer satisfaction. Send feedback. History. Saved. Community.
Linear regression essentially is fitting a line to a bunch of data points. And more technically speaking, it is fitting a function against a bunch of data points. So you can use linear regression to be able to predict future numerical values. Linear regression is important because it forms the basis for a lot of machine learning and deep learning algorithms. So what happens is that if you look at the math behind linear regression, you see how it is a core building block in a lot of advanced machine learning and deep learning algorithms. So when you understand linear regression, you understand basically a very core building block in other machine learning and deep learning algorithms. In this video, we'll talk about linear regression and why it's the foundation of all regression problems.
With its roots in statistics, linear regression is essentially a supervised machine learning algorithm where the predicted output lies on a constant positive or negative slope. It is a great starting point for us to start learning about the other machine learning initiatives we'll cover in this course. In this video, let's find out how linear regression applies to the machine learning space. Send feedback.
The first machine learning technique is probably something you may have already learned in school, particularly if you studied statistics. Linear regression is a great starting point for us to start learning about the other machine learning initiatives we'll cover in this course. In this video, let's find out how linear regression applies to the machine learning space. Let's say Chloe wants to sell her house, but she's not sure how much she should sell it for. She doesn't want to price it too high and scare away potential buyers. Neither does she want to price it too low and lose out on potential profits. She starts researching how much similar houses have sold in her area. With the research, she's been able to build a data table. For this example, let's take a look at a sample of 5 different houses. The houses are listed in order of their proximity to the city. House 1 is the furthest from the city but the least expensive, and House 5 is the closest to the city but the most expensive. Chloe's house is situated away from the city, but not too far so that the commute to work is too long. To accurately predict the price of Chloe's house, you need to know 2 critical things. We've kept it simple and just looked at the physical distance of 4 different houses from the city and their reported prices. So, how much do you think Chloe's house costs? If you guessed $400,000, you're right. In this straightforward example, the cost of each house seems to increase by $100,000 as it gets closer to the city. There's a direct relationship between price and distance. You've just performed a very simple function of linear regression. With its roots in statistics, linear regression is essentially a supervised machine learning algorithm where the predicted output lies on a constant positive or negative slope. Linear regression is used to model a linear relationship between the independent and dependent variables. Based on this linear relationship, we can predict numerical values, like the sales prices of the houses in the earlier example. The model's ability to learn from the data and adjust the weights as it learns is what makes linear regression a machine learning algorithm. There are 3 types of linear regression: simple linear, multiple linear, and nonlinear regression. Nonlinear regression is used to model a nonlinear relationship between the independent and dependent variables. This is quite complex and goes beyond the scope of this course, so we won't be covering nonlinear regression in this course. In this chapter, let's focus on the basics of linear regression, beginning with simple linear regression. Let's first identify what independent and dependent variables are. Independent variables, often denoted by X, do not depend on the change of other variables. In the housing prices example, the distance from the city is an independent variable because nothing can change the physical locations of the houses.
take long. You shouldn't spend all your time crouching. You'll hurt yourself.
Just a sec. This won't take long.
Dependent variables, often denoted by Y, are affected by the change of other variables. The prices of the houses are dependent variables because they are influenced by many factors, including distance from the city. This supervised machine learning technique can predict the numerical value of a dependent variable based on the value of an independent variable via a straight line through the graph called a regression line. The relationship between the independent and dependent variables are known as correlation. We mentioned 3 types in Chapter 2 on feature selection and engineering. Correlation is always represented with the term R. The level of correlation is always represented as a numerical range, starting at 1 for positive correlation, 0 for no correlation, and -1 for negative correlation. To predict the type of correlation between the independent variable and dependent variable, we can refer to the gradient of the line. If the independent variable and dependent variable are positively correlated, the trend line tilts upwards. But if the independent variable and dependent variable are negatively correlated, the trend line tilts downwards. If the independent and dependent variables don't correlate at all, the points on the graph will not form a straight line. Linear regression may not be appropriate for this dataset. There are another 4 types of correlation for linear regression we must know: perfect correlation, strong correlation, weak correlation, no correlation. To derive the type of correlation, you need to calculate the Pearson correlation coefficient, also known as the value of R. The value of R can fall within a range of -1 to 1 and determines how strong or weak your correlation is. Do note that while you can use software such as Microsoft Excel to calculate the correlation value, each software may adopt different correlation functions. The most common is the Pearson correlation, but there is also Spearman, Kendall, and others available. If members of your team use software with different correlation functions, you may end up with differing correlation values, which could be confusing. When calculating the correlation value, do make sure the standard correlation function used is communicated to the rest of your team. The main objective of linear regression is to find the line that fits most of the data points. We call this the line of best fit. How do we find the line of best fit? We use a formula called the ordinary least squares method. You may have seen this equation before in elementary math as y equals mx plus c. In linear regression, the formula looks like this. This method finds the line of best fit that explains the potential relationship between an independent variable and a dependent variable. We can use computer software, like Microsoft Excel, to calculate this equation, so we won't explain the math, but we'll clarify the process. When we enter data into the software, let's take the earlier housing prices data as an example. The computer churns out a scatter plot of the data. What do you notice about the scatter plot? Yes, this is a negative correlation because housing prices get cheaper as the houses get further from the city. Simple linear regression is perfect for this problem because the data points more or less appear to be following a straight line. Next, a line, using the equation we saw earlier, is drawn through the data points. The distance of each data point from the line drawn is calculated. Each distance is called a residual. The computer squares each of those residuals and adds them up. The computer proceeds to tilt the line up and down, or move it left and right, and repeats the same process of squaring the residuals and adding them up. The computer finally settles on the equation of the line that gives the smallest value. That's why this method is called the ordinary least squares method. The best fit line, or regression line, is now ready to be tested using new data points and evaluated for accuracy. Remember, this is the line of best fit, not perfect fit. The regression line doesn't need to fit all the data points perfectly, which may be a symptom of overfitting. On the other hand, if the regression line misses most of your data points, your predictions will likely be inaccurate. While correlation is an indicator of the relationship between an independent and dependent variable, it doesn't explicitly explain the effect the independent variable has on the dependent variable. For that, we use something called R-squared. R-squared is a measure of the extent the independent variables can be used to explain the variation in the dependent variable. In simple terms, it means how much influence the independent variable has over the dependent variable. This equation can be calculated by software like Microsoft Excel. But what you do need to know is that the R-squared value lies on a spectrum between 0 and 100%. An R-squared that is closer to 0% indicates that the independent variables cannot be used to explain the changes in the dependent variable. On the other hand, an R-squared that is closer to 100% indicates that the independent variables can be used to explain the changes in the dependent variable. In summary, linear regression is a form of supervised machine learning that tries to establish a relationship between an independent and dependent variable using a line of best fit. Linear regression is used to model a linear relationship between the independent and dependent variables. Based on this linear relationship, we can predict numerical values, like the sales prices of the houses in the earlier example. The advantages of linear regression are that the procedure of analyzing the data is relatively simple to carry out, and the results are easy to interpret. However, linear regression predictions can be negatively influenced by outliers. Outliers need to be weeded out through adequate data preparation. If the data is non-linear in nature, or the output is not a numerical value, linear regression will not produce accurate predictions. It is essential that you know what kind of output you need for your use case and use the appropriate machine learning model to achieve those results. In this video, we've only touched on doing simple linear regression with one dependent variable and one independent variable. In the next video, we'll show you how to use multiple independent variables in linear regression. This increases the predictive power capabilities of the model. We call this multiple linear regression.
Mission complete. Anything else?